Cool. Okay, so hi, it's directed graphs. Okay, so I hope you guys are familiar with the concept of graphs. Okay, I won't be going too much into them because we've already had a class on graphs. But the point is, they're a set of vertices, which is what these nodes are called. I think in some settings you might see them called as nodes, and the lines joining them are called edges. Okay. This is a regular undirected graph, which is probably what you're more familiar with, which is where edges don't have a direction. Okay. That basically means I don't discriminate between an edge from I to J or an edge from J to I. Like that doesn't make sense in undirected context. But in a directed context, I just add this additional element of to every edge, I also assign a direction. So, for example, in this graph, this is what's called a cycle because if I start at this vertex, I can go here, go here, go here, and then go here. Okay, and that lets me go in a path. Okay, that ends at the same vertex I started. Whereas in this directed graph, I can only go in one direction. So I think a very good analogy is just imagining cities and roads. So generally you're used with two-way roads. So if I'm in city A and this is city B, I can go like from I can take the road to go from A to B and I can take the road to go from B to A. But sometimes you'll have one-way roads, which is what directed graphs are like, where all the roads are one way. And like if we had a two-way node in a directed graph, we would indicate that with like arrow on both sides, but we don't deal with them in the stuff that we're going to be discussing today's class, which is arrows. Okay, arrows. Okay, so everyone clear on the definition?
Mm-hmm.
At least how a directed graph is just an extension of an undirected graph. So this is your directed graph, and this is your undirected graph. Okay. I hope you guys are familiar with undirected graphs because that's kind of nice to have. If any of you are not, you can ask stuff like anytime in between. Okay. Is everyone okay? Um,
Yeah.
Yeah.
yes. Okay. Cool. Cool. Okay. So, oops. Yeah. Okay. So now the philosophy of arrows. Um. Yeah. Okay. So the philosophy of arrows is to consider graphical equivalence of certain properties. So most of what we're going to be discussing today is going to be related with functions. But yeah, it's generally in terms of so what you basically are doing is, oops, what you're basically doing is that very often what you want to do is you see a non-combi problem, okay, and you try to reduce it to something that is combi. And a very good thing for this is graphs, okay, because sometimes you're just dealing with properties between elements, and that can be translated nicely into graphs. We'll get into examples briefly. And arrows is especially useful when you're dealing with algenty, okay, because it tells you to look at certain sequences. So yeah, arrows are actually more useful in sequences of at most countably infinite elements. Okay, so you're not going to see a lot of arrows in R to RFE, okay, but you will see them in Z to Z, um, N to N, N to N, and like sometimes just not even FE, just some sequence okay, sequence problem. Okay, so is Are we clear on? Okay, well, so this is just the inherent idea behind arrows. Okay, or where arrows you want to use. So it's not for R to R. Not usually, at least. Not usually. There are scuffed examples where you may use arrows in R to R. I did one recently, but we won't be covering that in today's class. Okay. Okay. So now we will discuss arrows. What is the idea of arrows? Um. So I think the best way to do that will be that we start off with the problem itself. Um. So we take this. Oh, by the way, how many of you are going for InmoTC? I think that's starting like soon. Like Karnataka, I know it started today.
I am.
And, mhm.
I am too.
This the handout I'm actually referring for today's class is was actually given to us at my InmoTC. So we're going to be using that. So yeah, this is P1. Okay, so this is P1. Um, yeah, so A1 to AN is a sequence of real numbers. You guys are not scared by TSTSTs, right? Like it's scary, but don't be. This one's easy. Trust me.
Is that harder than TST or
No,
easier
no,
than
no. Team
TST?
selection test, selection test. Okay, so it's
Okay, so
what
easier
gets
it
you
is.
call it. Yes, it's easier than TSTs. It's easier than TSTs. But I'll be honest, it's harder than INMO. Okay, so P1 in the TSTSTs could be like a P5, P6 INMO, maybe P4 on a stretch.
No,
But yeah,
like
these are
USAMO is harder than INMO. So this
yeah,
is
yeah.
more hard.
This is harder than USAMO. Problem wise. So like a TSTST P1 is going to be easier than USAMO P3. Okay, it's going to be closer to USAMO P2. Okay. But yeah, that's just hard in more. Like hard in more. But these are problems that are nice. Okay. Anyways, so y'all can read the question. Okay. So we have this sort of sequence of real numbers. Okay, so we'll start discussing how can we convert this question into graph related stuff. So does anyone have any ideas? I guess should probably use this more as an example, right? So I guess one very nice thing when dealing. Okay, so what do you see about properties of this sequence? Does a cyclic shift of the sequence really change anything? I'm sorry if I'm going a little too fast. Have you all read the question? Are you all like clear with what the question's asking?
Not yet.
What?
Not yet.
Okay, fine, fine. Take it out. What are you doing? Okay, there you go. A1 to A. Okay, so question one. Uh, what if no, actually m equals 1. This question one doesn't use arrows. It's honestly just to see if you have understood the problem. And this is generally, I think, something that I would recommend for this type of problems, at least, where like you have some parameter that is variable. So, for example, m here is a parameter that's variable. N here is a fixed integer. Okay, this is your base case sort of thing, and m here is some sort of free parameter that varies on n. So generally, a good thing to do is you want to just check for like trivial values of m to see if the question makes sense so that you can understand. So tell me when you guys are done with Q1.
In Q1, just the definition of AK implies the result, right?
Yes, just the definition of AK implies the result. So yeah, that's what I said. You want to just check out small cases so that you have the trivial ones out of the way. So yes, this basically m, m equals 1 implies AK greater than equal to 0 implies K belongs to T. Okay, and it's a Y, so it's a two-way thing. So therefore, summation of AK overall K belongs to T is equal to summation greater than equal to 0 sum, yeah, K belongs to T, which is obviously greater than equal to 0. Basically, we're summing over some greater than equal to 0 stuff, so that will always be greater than equal to 0. Does this make sense?
Yeah.
Cool. Yeah, so that's m equals 1. Okay, so now we'll start by thinking about how can we. Okay, so why do I want to even think about graphs? That is because of this nice property where indices are taken modulo n. Okay, so if I really think about it, what am I doing? I'm looking at this, looking at this, I'm looking at this, dot dot dot. Have a couple of elements in a ring. What I'm really looking at is I'm just looking at arcs. Okay, and like sometimes, and I think that's really the hard part about some of these problems, and just to show how powerful it is that it's hard to think of arrows, but once you do, it can almost always just almost always just finish the question. Like if it's arrows applicable, there's not a lot you want to do. So we'll consider this, and what we're basically telling is there's a segment of length less than equal to L, less than equal to M. So this is less than equal to M in length, such that this sum is greater than equal to 0. Okay, and I want the starting point of each of these segments. Okay, if the starting point of each of these segments is negative, right? What can you tell? Is there, like, say that this is a1 and a1 is less than equal to 0, let's say, but 1 belongs to T. Can Does 2 belong to T?
Yes.
Why?
Because if we keep the same L, then A2 plus up till A1 plus L minus 1 would be greater than equal to A1 plus A2 plus the rest, because A1 is negative, and we know that thing is greater than equal to 0.
Yeah.
So A2 is also means 2 also belongs to T.
Yeah. Okay. That's fine. Okay. So that's the argument for that. Okay. Now let's see. What do you want to say next? Uh, okay. So now let's look at the set of all. So let's look at the set S, okay, which is a subset of T, such that K belongs to T, ampersand AK less than equal to 0. Okay, everyone okay with this? I'm looking at this set. Okay. Uh,
Yes.
okay. So now, oops, what is happening? Yeah. Okay. So now say that this is less than 0. This is less than 0, and now these are greater than 0. Doing points. Okay. So let's just start with this point, right? Okay. Now this is in some arc, right? Some arc. So this will be like AK. So this is AK, and let's say that this is AK plus L minus 1. Okay. Um, such that this is less than 0. Okay. Now, can you have, okay, and now what I'll basically do is I'll try to fit this into a set of arcs. Uh, okay, wait, what do I want to say? I want to introduce the arrows idea, right? What do I want to do? Okay. Okay, so now what I'll do is I'll just imagine this sort of long arrow which connects all elements in each arc. Or, yeah, yeah, fine. Mm, yeah. So I just consider this sort of long path which connects elements in each arc. Um, can you have an arc inside an arc?
Could you please
Uh,
repeat the question?
yes. Okay. Can you have a smaller arc inside an arc? Like for example, let me actually just expand this. I think that might be smarter. Just discovered that 3 elements is not enough. So say that your arc was like this long. Okay. Now, could it be possible that these 3 elements are an arc? If you think
Yes,
yes,
I
you
guess.
okay. Yes. Do you? Yeah. Basically, the answer is yes. Okay. So what we just want is we want maximal arcs. Okay. So basically, what I want is ignore arcs inside. Okay. I just want sort of maximal arcs. Okay. So basically, I consider a set of arcs so that no two arcs are, you know, such that every I want to consider a set of arcs so that every AK less than 0 is in some arc. Okay. So basic. Oops.
Like, do I partition the set of all vertices into like arcs? Like, no vertex will be left
It's not a
alone.
partition. It's not. I mean, it will be, which is what we want to show eventually, and I'll get to why that's what we want to show. But right now we
Mm-hmm.
don't know if it's a partition.
Okay.
Okay. Okay.
So we
Okay.
could have
But
arcs like the one which you showed over here in this example where they kind of intersect. They have a common overlap.
these two arcs, right?
Yes, yes.
Yes. Yes. So at the moment, yes. At the moment, yes, we can have such arcs.
All right. Yeah.
Okay.
Yeah.
And I'm just yeah. Okay. So and like arrows here are just going to represent connections from start point to end point, or let's actually just denote them as like the sort of colored path. Like let's use some different color for these guys. So now this oh, that's not visible. Uh, the, 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 the. Okay, now say that two arcs didn't. Say that two arcs did intersect. Okay, can you say anything about this segment? What is it I wanted? This is this positive. This nothing is positive. Okay, wait, I want this. It starts. Okay. Mm, okay, wait, I want to be a little smarter in how I'm constructing my arcs. I will so basically what I'll do with my arc construction is I'll take the smallest. So I'll start at a vertex, and I'll take the smallest value till which it's less than equal to 0. Okay, so for till here it's going to be less than equal to 0, and then this will be the first time it's greater than equal to 0. So I can always choose L like that, right? Does this make sense?
Like the smallest cell, right?
Yeah, yeah, basically I'm choosing the smallest L for each k. So I started this, I choose the smallest L, so now I'm here. Okay, and I know that for all of them it's less than equal to 0. Then I go to the next negative value and I start there, I choose the smallest L, so this is less than equal to 0, and this will be greater than equal to 0, and this will be greater than equal to 0, and I repeat that for all of them uh, until I reach here. Okay, so what can you say about this intersection segment? Can you comment on whether the intersection segment is positive or negative? Probably want like a larger.
Intersection should be negative because it is also the starting point of another arc.
Yes, we have the fact that no arc is contained within another arc. Okay, because we just choose the largest, like the smallest covering set. Okay, so therefore no arc will be covered entirely within another arc. So therefore if two arcs intersect, the start point of one arc is before, like, so it will be start, start, end, end. Okay, so this will be start 1, start 2, end 1, end 2, right? So this segment I know has to be less than equal to 0. Do you agree with that this has to be the order? Because start 1 has to be before end 1, and if they're intersecting, end 1 has to be after start 2. And now if N2 was before end 1, it has to be after start 2. So if N2 was before end 1, then S the second arc would be contained entirely within. So all arcs, all intersecting arcs are going to be of this form. Okay, which means that start 2 to end 1 must be less than equal to 0, as otherwise I would have just ended S2 at end point 1. Agree?
Yeah.
Okay, so now I have that this is less than equal to 0. So what can I tell about this segment?
To be greater than or equal to 0.
Okay, but what did I say about this length L? Okay, about its minimality. Like, this is minimal, right? So can this be greater than equal to 0?
So we get a contradiction.
We get a contradiction. That, and what was my assumption here?
That they intersect.
Y- that they intersect. So when I force this sort of idea of I want this minimal L, what additional property can I get?
No two arcs intersect.
No two arcs intersect. Beautiful, right? Okay. So now what does okay? So now it's this sort of arc stuff, and they all start at this. Do I want anything? Okay. Yes. So now I have a bunch of non-intersecting arcs. Okay. Um, what can I say about every positive here? Um, okay. And now what can I tell about every point in an arc? Okay. My following claim is such: uh, if point P belongs to an arc, okay, then P belongs to T, or like if AP belongs to arc, then P belongs to T. This is claim. Does anyone have any idea why? So I want you to show me that this element belongs to the arc. Belongs to, so like if this is A1, A2, A3, dot dot dot, then my claim is that A3 3 belongs to T, and we're only using the things that we have said so far. Does anyone have ideas why?
Then we get a minimality violation again. Maybe
What?
um, if we delete the vertex AK or AP,
Uh-huh.
then we will get at least one arc or two arc. Uh, uh, so one of them must be greater than or equal to zero, which is contradiction.
What should we? No, I don't know if an arc starts at A3. So I can't say A3 to A. So this is A5, this is A4. So I don't know if A4, A5 greater than equal to 0. A4 plus A5. So if this breaks into an arc, that and this is greater than equal to 0, right? That's fine. Is that what you're trying to say? Like if you remove this element, this will be less this like you'll have that one of them will be greater than equal to 0. Was that what you're saying? Hello?
If we select from AP to rest of the arc,
Uh-huh. So that's
then
this.
we'll get a sub arc if its value is less than or equal to 0, then
Mm-hmm.
the initial arc
Yes,
will be greater
precisely.
than or equal to 0.
Yeah. This is what I wanted. I think I misunderstood you initially said. My bad. Yes. So the point is this.
Or might
So for any vertex
be
on
wrong.
the arc, if it till the end of the arc is less than equal to 0, then the start till just before that point will be greater than equal to 0. Okay. So therefore that's a contradiction because I've taken the minimal length arcs. Okay. So every point on the sorry, every point on an arc should be greater than equal to, like every point on an arc should belong to P. Can you conclude the question from now? So use this claim and then use the non-intersecting. non-intersecting arc, and then use the fact that arc sum positive greater than equal to 0. Using these three, can you all finish the question now? It, if you want, the question is to show that sum of k belongs to T is greater than equal to 0.
Yeah, I got it.
You done?
And
You want to
can you
explain the proof?
say some motivation?
Yes. See, so this is a TSTST question because this is hard to motivate. Okay, but here's the rough idea. The motivation behind arrows, which I think I'll illustrate through this example here, is that we want to visualize. We want to visualize things. Visualize things. Okay, and this is a very combi motto. Like, this is when I think combi, I just want to visualize the thing so that I understand what's happening, and then I just want to be done with it. Okay, so all of this sequence business, very cool, but this property, I'm not able to understand it very well. Okay, so what I want to do for that is I want to look at this sort of set of what can I do. Okay, so that's going to be the first motivation. So this motivates the idea of points on circle, points on circle. Okay, and the circle bit is due to modulo n indices. Very often, if you have stuff with modulo n indices, it's worthwhile considering them as points on circle. Okay, at
Mm-hmm.
least think about that once. Okay, especially if you like this sort of idea of visualize and work with stuff. Like all of this stuff that I've written here, like arrows is entirely a philosophical method. Okay, like I'm not going to go into philosophy right now because that's not what the class is about. But at the end, I would say it's very similar to how fair few bit of, I don't know. Yeah, you generally won't write arrows in your final solution. Like you won't say that we consider the following arrows. It's what you're using to solve the question, and then in your final write up, you might like actually make this all algebra like in no combi, which I despise. I will write like the full combi style proof of this. But yeah, the idea here is that you want to when you're solving a question yourself, you want to be able to visualize the question in your head so you can understand it better. It's like, so you basically want to, like, the point is I don't know the, so I guess the idea is that I don't know what's happening in the in the question. So what I'll do is I will manipulate certain properties, certain properties, and see if I can extract more information. And this is why I said that initially also, if arrows work on a question, work on a question, it makes it a lot easier. Lot easier. Okay, or whatever I said. Okay, so arrows is like a could work, may not work thing because you need the freedom to manipulate properties and you need to be able to extract more information from that manipulation. So an example of how we did that was that we manipulated the property of exists some L to exists minimal L. Exists minimal. Okay, and by taking that minimal L, okay, I managed to extract two properties. I managed to extract the property that the arcs are non-intersecting, and I managed to extract the properties that AP belongs to arc implies P belongs to T. Okay, so these are two properties I extracted from this single fact manipulation. Okay, and very often you like I guess this is just more extremal combi side. But very often, if you have exists some L, you might want to consider minimal, maximal, whatever seems to make things nicer. And a very good way to figure out what makes things nicer is also figuring out which side is the more easier or trivial, if there exists an easier or trivial side. Because, for example, since I tried out what if m is equal to 1, okay, I guess that maybe, smaller things are nicer. And that motivated me to consider minimal before maximal. Before. And later I may have considered maximal, but we solved the problem, so yay. And this is generally true, like if m equals 1 is quite easy and like m equals 2 or 3 or small m is easy, then there is a chance that this taking the smallest L might make things easier, because you notice that m equals 1 like restricts the question very strongly. So then maybe m equals like taking the smallest L also restricts the question strongly. Okay, so yeah, this is an illustration of arrows in non-FE. I wanted to do one so that we know that it's not just an FE thing. Okay, and now we're going to do FE with arrows.
Excuse me.
Yes,
Uh, could you please explain how the three facts implied the solution?
yes. Wait, which one of you is the one that got the solution? Do you want to explain?
Yeah,
Uh,
mm,
Anik.
got.
Yeah, you can explain. I
Mm,
think.
Actually, we get that some number of non-intersecting arcs. Yeah, and am I audible?
Yeah, yeah, you're audible. So,
Uh, so in every arc, all the points are good, which we have just proved now.
okay. So, AK, AP. Okay, so you can look at it like this. So I think now this might make things easier. Okay, does property 1 plus property 2 imply this is greater than this thing is uh, greater than equal to this thing? And can someone also explain why this is not a direct inequality? Not equal to. I mean, you could make it equal to, but like doesn't really matter. Okay, Anik, can you explain why AK is this sum?
Mm, all of the numbers on the arcs are good.
Wait, what are you
Then
calling a good point? What are you calling a good point?
uh, in the question, actually,
Oh
the
wait, they
definition
have
of
they
good point.
defined good? Oh yes, okay, okay, fine. They've called that good. Yes, my bad. Yes, okay. So yes, every point in the arc is good, indeed.
And uh, we take the sum of the good points, actually.
Yes, we're
Actually,
taking the sum of good points. What are good points not on the arc? Are any good points not on the arc negative?
uh, no, actually, they are not good points.
Yes. So if a negative point was not on any arc, then it can't be a good point. since otherwise it would have been like we would have made an arc that started at that point. Okay, because of this. Okay, so therefore AK is greater than equal to this thing, and there could obviously be like some good points which are positive because we don't construct arcs for those points. Okay, so therefore we have this inequality. Okay, because this takes every AK and that's part of exactly one arc. Okay, so this is not, this is across B belongs to A. Yeah, and that each AK belongs to exact at most one arc. Okay, and it belongs to one arc exactly if it's negative. So we have like the sum of AK, K does not belong to any arc, which is greater than equal to
equals
0
to
plus AK belongs to some arc. Okay, and this I can split, K belongs to some arc, and this I can split into taking each arc. Okay, because
But
every
in
AK
the
is in, huh?
like in the first one, then L becomes 1. Like if K is not a part of any arc, then L is just 1, right?
Yes, yes. So there will be no arcs.
Yes, okay, understood.
Understood. Yeah. So yeah, we have this thing, and what we're basically using is that this sum is greater than equal to 0 for each arc. This is just by definition of the arc. Like it's the minimal value so that this thing is greater than equal to 0. So an arc sum must be greater than equal to 0. So we're summing over a lot of positive things. Summing over greater than equal to zeros. Okay, so therefore we have that the entire sum should be greater than equal to 0. Does that make sense?
Yes.
Okay. This was your proof as well, right? I didn't deviate from that. This was your proof as well, right? I hope I didn't deviate from that.
uh, yeah.
Okay, cool. Yes. Where's the next problem? Yes. Okay. So yeah, we'll be now doing some FE, which is very cool. Uh, Ideally, I would like to build from this FE to something else, which might take more time than what we have. So class might get a little bit extended, but you're free to leave at 8:30. We'll finish this problem at least, which should give you guys the FE intuition of arrows. Okay, so previously we had things happening modulo something. We had things happening here that was modulo n. So how would you think graphical interpretations would work if we didn't really have a lot of modulo conditions? Um, can any of you guess how the graph might look? Again, the a huge factor is considering graphical equivalence. But for these type of problems, I will show you why it's nice to consider graphical equivalence in a brief moment. Or like once we're done with this question, I'll show you why it's nice to consider graphical equivalence. Okay, but I want you all to say what do you think the graphical equivalent would look like, or at least how would the vertex, what would the vertices be?
I think it's like the mapping of functions, as in like something from the domain to the range, as in like that. And then you can show that uh, suppose an arrow from one vertex to another shows that f of that yes, so f of that
So,
value is such.
so this is x and this is f of x. Is that what you're saying?
Yes.
Yes, and that's exactly what we're going to consider. Okay. So here's what we're going to do. We're going to take all the z greater than equal to 0, 0, 1, 2, dot, 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 till whatever. Yeah, basically, we're just going to keep going. Okay, so I'm just going to take 2023, 2024, dot, dot, dot. Okay, so now I know my arrow is going to go somewhere. Let's just say that 0 goes somewhere, and that something has to go to 2023. Agree?
Yeah.
Okay, so now let's try our FE manipulation to see if we can get any further information. Okay, about these arrows specifically. So what I particularly want is I want info on f of n. Okay,
Yeah.
right. So can someone try to force f of n to exist somewhere, like just f of n, not f of n? And yeah, we just want to get some information on f of n.
F cube of n equals to f of n plus 2023.
Oh, wait, can you speak a little bit louder? I'm so sorry, I didn't hear what you just said.
Uh, F cube of n equals to f of n plus 2023.
What? Can you repeat? Like, I'm so sorry.
Actually, f applied 3 times equals
Oh,
to
f. Okay, yeah.
f
So
of n.
okay, f3 of n is equal to f of n plus 2023, right?
Yeah.
Okay, but now can you equate f3 of n to something? Also, if you have done this problem already, I'll just give you the next segment so that you can start working on them. In the meantime, you guys can try to figure out what else f3 of n is equal to. F of a n equals b equals b. What did I need? Zero until a b minus one. Okay. Yes. Have you guys? This is the problem. This is the show. If this is true, then the following two statements are true. Okay. These are just sets, so they're not pointwise equal. Okay. Just want to. Oh wait, this will be a. This a. Just give me a second. Let me just partition into the others. Yeah, this is actually stronger than this. Wait. Oops. Have any of you got what this thing is? Um, f3 of n. Some other way to represent.
F of n plus 2023.
Yes. Okay. N plus 2023. is this thing. Uh, just give me a second. Can be partitioned. Can be partitioned into. Yes. Okay, this is the statement. So this can be partitioned into this such that this holds. Yes. Okay. So what does this mean? What does this mean? Um, f of n plus 2023 is equal to f of n plus 2023. Can you figure out something more from that?
I understand where f of n plus 2023 is equal to f3n. I'm not sure about how it's equal to the last expression,
Yeah.
the
Okay.
third one.
Yeah. So that's a little trick. Uh, that's called the FFF trick. It's something that you should be definitely familiar with. So I just say this is equal to n plus 2023, right?
Yeah.
So I'm just replacing that here, like the fact that double f n is n plus 2023.
No, I understand the why how the first expression is equal to the second
Oh,
expression. Not
oh,
sure.
oh, you mean this equality?
Yes, yes.
That's just replacing n with f of n here. Like I'm just replacing n equals f of n. But if you don't
Oh,
like the
right, right.
two
Yeah,
variable notation, this is f of m, and then I'm saying m equals n later on for like niceness.
yeah. Okay, I see. Mhm.
Okay, so that's how we get this second inequality. Okay, okay. So now what does this do? Yeah, I'm so sorry by the way. I don't read the chat very frequently. You can probably just speak out if that's fine. Uh, yes, f of n plus 2023 is equal to f of n plus 2023. Now, can you use this to get some more info?
So we could map every one of these vertices which we have to f of n plus 2023 if we assume f of n is equal to some n m.
Wait, can you repeat?
Like we can, since we know this functional equation, we can kind of map it. We can kind of see it in our graph now,
Yes.
right?
Okay. So, what is the graph that you want to really consider? Is it all integers, or do you want something a little bit nicer?
Nicer as in, I'm not quite sure what you mean by that.
Can you work with the graph modulo 2023? You use
Okay.
this to work with the graph modulo 2023. Like f of 2024 will just be f of 1 plus 2023, right?
Right. So we can say that for every modular residue of 2023, that maps to each. So f of 0 maps to f of 2020. So 0 maps to 2023 and so on, like that.
0 doesn't wait. 2023 is 0 itself. Like this will go to
Right.
2021,
Yeah.
2022. Okay, so f of 0 is going to be something. Okay, so that's going to be mapping to some I here, right?
Right. But if
And
we
I has to
expand it
map back
out,
to 0. Do you agree?
yeah, yeah. Hmm.
Does 1 similarly have to map to some j?
Oh, wait. How did you get that cycle from 0 to 2 or so? I suppose.
No, it's I. Like this is just some vertex here, which I'm calling I.
Okay.
Okay, now f of 0 is I modulo 2023. Okay,
Right.
so there's two cases. So case 1 is I not equal to 0, I not equal to 0, or case 2 is I equals 0. Okay, or more accurately, I just want to look between two vertices I and j actually. Now if I just have vertices here dot dot dot, now if I have I and I have j, and say that f of I uh, is equal to j mod 2023. Okay, then f of j is congruent is equal to I mod 2023.
Yeah, yeah. Okay, okay, I see.
So this is your cycles. Okay, can j equals I? Can j equals I? Can this happen? Or can you show that this cannot happen?
I guess this is similar to proving F is injective.
This is very similar to proving f is injective, but just that it's injective modulo 2023. It's not injectivity. Injectivity is fine modulo 2023. This is just can it be itself modulo 2023. Okay, assume that we had that this was false. This was false. Assume, assume. Can you finish the question from there? If j equals I was false. Can you see why the question's done?
So, right. So f of I is equal to is congruent to j mod 2023. But what we're saying is that f of instead of n plus 2023, I'll take that as I. Then we can say that's f of I plus 2023.
Wait, f of I plus 2023 is equal to f of I plus 2023. Okay. What are you saying?
So, like, I was a bit puzzled about the I to j, j to I thing because if I is going to map to f of I is equal to f of I plus 2023, like that, and so on.
Oh, wait, that's right. Uh, f. Wait, I didn't understand. I didn't follow.
So, like, if I'm taking from zero till after 2022 on and on continuously, like what we had before,
Okay,
not
okay, fine, fine.
forwarding.
Okay, okay, my bad, my bad. I was thinking of the modulo graph. Yes,
So, zero would be mapping to 2023, one would be going to 2024, right?
yes. But that's not directly. That's after two iterations. So
Yeah, that's
zero
after
maps
12.
something, and then it then maps to 2023. Yes.
So, how can we say that f of if f of I is congruent to j mod 2023, f of j must also be congruent to I mod 2023.
That's literally this condition. Because we are adding 20, like, so f of j is equal to f of I, which is equal to I plus 2023. Okay, so f of j is equal to this thing mod 2023 as well.
Okay, yeah, so then the 2023. Oh, right.
2023 just vanishes. That's why you have this.
Okay.
So this implies this f of.
Here are the INJs less than 2023.
Yeah, I and j are less than 2023. So it's 0 to 2022. Now the only thing that's left to show is j not equal to I. Can someone show why j not equal to I finishes the question?
Then, actually, no, wait, just a minute.
So I
Got
Assume
maps
by
that
to
j was
j.
injectivity.
never equal to I. Assume j was never equal to I.
I think I have got by injectivity.
Injectivity.
Yeah. If
You
we
mean
take
you mean
f
that?
of
Yeah, just tell.
um, if we take f of a is congruent to f of b,
F of a. Yeah, f of a congruent to f of b. Let's say is equal to c.
then
Then you have f of c is
then f
congruent to.
square is
Yeah, so you'll have that it's injective modulo 2023. would be congruent to both A and B simultaneously mod 2023. This is what you have, right?
Yeah.
Okay. But I'm just telling that f of I is congruent to I mod 2023. Why is this bad? Like, this is not related with injectivity. I'm telling that there's no J. J is just I. So f of I is congruent to I mod 23. Why bad? Like, I'm not saying f of I is I and also f of J is I
So,
again. No,
and we
I'm
know
not.
that f of I is congruent to J mod 2023. So,
No, no,
I
no,
and
no.
J.
There's no J now. There's no J now. There's no J now. Like, J is just I. Like, does that make sense? Like, I want to show that J and, like, see, I have that f of I maps to J, and f of J must. So this implies f of J is I.
Right, right. Yeah.
What I just want to show is that J and I are distinct. Okay,
Yeah,
that's what
because
I
that
want to show.
finishes the problem. That finishes the problem. Okay.
Yeah, that finishes the problem. So I just want to show f of I and f of I cannot be I mod 2023. Can someone show me why? Can someone tell me why?
I think I've got one.
Mm-hmm.
Uh, we consider f of I equals to I plus 2023k.
F of I equals I plus, yeah, 2023. Okay. Okay, yeah, yeah.
Okay.
So now f of I is equal to f of I plus 2023k, which is equal to I plus 2023, which is equal to, this will be f of I plus 2023 times k, and now f of I is just I, so this is equal to I plus 2023 into 2k, and therefore this implies 2k equals 1, which implies k equals 1 by 2, but this is a contradiction. Okay, because this is a
Yeah.
z greater than equal to 0 to z to 0. So half integers don't exist. Okay, this works. I'm sorry if I'm rushing things. I just wanted to finish stuff within class time. Okay. Um, does this make sense? Why can you not have I equals j?
Right. Yeah. Okay.
And this is not like an injectivity thing. I don't know if f of something is I. I just know that f of I itself is I. I don't know about anything else. So that's why the injectivity idea doesn't help. At least I don't know of any way the injectivity idea gives this condition. And obviously there are alternate solutions without arrows. I think there and all in injectivity or pseudo injectivity might help. Okay, and this finishes the problem because now I have a pairing of I and j. Okay, so now these are pairs I and j. Okay, and therefore you have, yeah, so these are pairs I and j, so 2023 elements get paired. Actually, you're using injectivity here. Let's get paired. uh, you're using injectivity here. By injectivity you have that I is in only one pair. Okay, is this cool?
Yeah.
Okay, now
Yeah.
can you show that if f of a is n plus b, using very similar ideas to what we just did. A divides B. A divides B. This is going to be the next bit.
A divides B if
F repeated A times is equal to n plus B. F of A times f of n is equal to n plus B. Okay, A times. I assure you my handwriting is a little bit better when I'm not using the writing pad. It's very similar to this thing here, just that we have replaced A and B with, I mean, so we have replaced 2 and 2023 with A and B. Also, just find the valid function as well. Find valid two. Okay. Mhm. This. Have any of you got anything on why A must divide B?
Right now, I just got the, like last time we had the expression, right, with the two equalities.
Which expression? This one?
Y- Yeah, yeah.
Okay, yes, so you got this expression. Nice, that's still a lot of work. So what you should have right now is f of n plus b is equal to f of n plus b.
Yeah. So like it's getting a bit, trying to find a way to get out of that and use the fact that A
So
is also.
when you're in those sort of situations, you want to look at the values modulo b.
Yeah, so I've kind of drew the graph,
Uh-huh.
kind of working with what happens for some residues I and j of modulo B.
Okay, so now here you want to go from ij to I1 till ia. So I1 maps to I2, I2 maps to I3 till maps to IA, and then IA maps back to I1.
Right.
Okay, now can you show that IM is not equal to IN? That is that all of these residues are distinct in each sort of cycle. And then you want to show that cycles are disjoint, which is just injectivity and like, which is basically the same injectivity proof. So that won't be difficult. The tricky part is showing that, you know, it's
I
again this,
am is not equal to ij. Sorry. Yeah, any variable works.
yeah, any variable works, you get the point. Yeah. So yeah, you just want the injectivity thing, and then you want to show that these loops are, you know, not containing themselves. And then from there, you just use the same pairing argument to get this. Have you got A divides B?
Not yet. I'm kind of getting stuck on the that part of
This bit, right?
going.
Of showing that indices are distinct.
Yes, yes.
Yes. Okay. Fine. So what did we use to say that indices are distinct here?
We use that kind of congruence part, right? So, and we are
Yes.
bringing the congruence using division algorithm back to an equation.
Yes. So say that Fk of I is congruent to I mod, what is it, B. Can you show that K divides A? Can we first show this? Can you do this? K divides A. So to reiterate, f of A
So f
times,
of ki is equal to I plus some bm. Okay.
wait, f a of I. Is this what you want?
Uh, f of k. No, no, like
Uh,
I'm bringing the congruence to an
oh, okay, okay.
equation.
Fk of I is equal to
Yeah.
I plus, what is it, bk, right?
Not necessarily k, right? Like we should use
Oh,
different
wait,
values.
wait, bad. Yeah, give me a variable
K
name.
is very common when we use that.
BL. Okay.
Okay.
Yeah.
So
If you guys have favorite letters, like please let me know. I don't have any of my own, so like variable names, we're out of them.
yeah. Then from there, okay, now we can take what we did last time was we took the f of that on both sides.
Okay. So we took f of that on both sides. Okay.
So I'm wondering, should we take f of a minus k now, or do we take f of that on both sides? Just that.
Uh, what do you want to do? Let's see. So now the point is, that this thing is, I would take f of a minus k.
Yeah, that's what I
Uh,
was thinking because we would like a f a somewhere.
f a. Yeah. So, oops. So then this will be f a of I. Uh, f a of I is equal to f a minus k of I plus bl. And then like the point is,
Now we can say that
this
as
is I plus b. So this is f a minus k times I plus bl. And yeah, the point is this thing I can subtract k from again. So this will be f of a minus 2k times, this will be like this thing plus some b dash l, right?
b dash. So how do
Uh,
you get the minus k part on both sides?
yeah, I didn't understand. See, I'm taking f of a, basically taking f of a minus k on both sides.
Right.
Okay. Now I'm using the fact that f of f bar k times I is equal to I plus bl. So I
Yeah.
plus bl, okay, uh, f bar k. Now the point is f of I plus bl is equal to f of I plus bl, right?
Right. Yeah. Hmm.
Right. So I can actually get rid of the entire bl. Okay. So basically what I'm doing is I'm taking the bl out of all of these f's. Okay. And I'm just writing f of a minus k times I. Okay. Of I plus bl. Okay.
Yeah.
But now f of a minus k times I can write as f of a minus 2k times f of k times I, right?
Yes. Yes.
Now this
Yes.
I can again take bl out. Okay, so I can write this as f of a minus 2k times I
Then you
plus
continue
b.
doing this on and on. Yeah.
Yes, so I can do this to like, and now this is why I wanted k divides a.
Yeah.
Right? This is gonna be a little bit tripped on how I would do this without k divides a. But the point is, once you know k divides a, I do it till f of a minus
Would there be
a.
a way if we assumed that it instead of a direct proof,
Yes.
assuming it or assuming the converse or something like that?
Oh, you want to prove this via assuming the converse. K
Yeah.
divides a.
Yes,
Okay.
assuming formulas of music, yeah, basically somewhere. This is the direct proof. So because the first thing I
You
think
want
in
to
my
know?
mind, yeah,
You don't need to do all of that. It's just uh, say that a is equal to, what is it? Tk plus r, right? So then f a I is equal to fr um f of tk times I. Now f of tk
how
I can
you
just write as
substitute
f
that.
of k, f of k, f of k, like t times,
Yeah,
right? And this is all just I. This will remain I. This will remain I. So this will just be f of r modulo I. And I just look at minimal k. So I'm just looking at minimal k
yeah,
actually. Again, yeah. So that's why k divides, because now I have that f of. So therefore f of r of I is equal to I, and r is less than k, which contradicts minimality, unless r is equal to 0. Unless r equals 0. So therefore, yeah, we have r equals 0.
yeah,
Okay, and therefore I have a divide and k divides a. So that gives me this thing. And obviously this tells you that uh, a by k times b is equal to 1. Okay, which tells you something like, yeah, k is equal to ab, but then k is also less than equal k is less than equal to a. So you have your contradictions here. Whatever. Uh, yeah, point is this works. This is the idea, at least.
yeah,
A sketch. Okay. Uh, there's a way you can prove it with the second condition, but we won't be doing that. Like we'll try to prove the second condition now that we know a little bit more of the first. I mean, you can do it without it. Basically, the idea is that the set of the first b elements can be partitioned into like these sort of loops that link within themselves.
mm-hmm.
Okay, and then it finally leaves the loop at the end. Okay, so
Mm-hmm.
for example, this is given that a divides b. This is now we know a divides b. Okay, which is why I said we need this to do this, but you can also sort of do from here to here if you just happen to assume a divides b. But yes, we use this to prove this. Anyway, so now that we have a divides b, we'll basically be trying to force in these loops. Okay, do you have any idea? So, okay, give me a function with like a equals 3, b equals 3.
Equals 3 b is equal to.
Yes.
So
But I
f.
don't want n plus 1. I don't want n plus 1. N plus 1 is boring.
So what do you mean? F of a is equal to 3 and f of b is also equal to 3.
No, no. F of 3n is equal to n plus 3. Like I'm just replacing a equals b equals 3
Oh,
here.
okay, okay.
That.
What kind of function of that?
Yes.
But
But
yeah, you don't want. I see why you don't want n plus one.
not n plus 1, man. Like that's so boring.
Yeah,
That's so
yeah.
boring.
I
I don't
see.
want
I
I
see.
don't I don't want n plus 1. Can you give
Uh,
me a function?
what kind of function of that? I don't know how to find these functions from thin air.
See, what are we really doing? We're looking at things modulo b, right? Like if you look at it, what we're really doing is we're just doing a lot of modulo b analysis, right? So
Mhm.
think about these things modulo b. So what would a 1 mod 3 look like? What would a 2 mod 3 do? And what would a 0 mod 3 do?
Wait, I didn't get how you got modulo into it. So you're saying f of f3 of n is equal to n plus 3 modulo 3?
No. F3 of n is n plus 3.
Uh-huh.
This is the condition. Yeah, I
So
want
where
you to
did the
just
modulo
construct a
come?
function. I want you to construct a function. And I'm motivated to think of modulo because, like, look at what we've been doing so far. What did we do for the first question? We looked at the
A
numbers.
modulo is a function. The modulo itself is a function.
Mod 20. What do you mean modulo is a function? Like,
Right, f of n is equal to is congruent to n mod 3. Very quite simple.
that gives n plus 1. Boo.
Oh right. Huh?
Wait. Okay, wait. You're saying itself. What do we discuss right now? What do we discuss right now? What have we been doing so far?
So like we were showing that they're distinct, right? So
We're showing that they're distinct. So
yeah.
why would one map to itself?
All right.
Right. So
I'm
we've
just
literally
trying to
shown.
like I was thinking solely of that function, not of what we're going to do about it for in that time.
Yeah. So for example, instead of n plus 1, which gives 1 2 0, or no, it gives 0 1 2. So for example, n plus 1 will give 0 goes to 1, 1 goes to 2, and 2 goes to 0. Okay. So instead of that, let's just reverse the loop, which is the only other way to do the function. Okay, because this is 3. So and it's like this, it's like this. So f of 0 is equal to 2, f of 2 is equal to 1, and f of 1 is equal to 0, which is given by the function f of n is equal to n minus 1 if, what do you say, 3 does not divide n, and f of n is equal to n plus 2 if 3 divides, wait, f0 should be 30 3 0. Yes, okay, wait, no. This will be n minus 1, n minus 1 if 3 divides n minus 2, 3 divides n minus 2, n plus 2, otherwise. Okay, so this is a fully valid function. Okay,
Yeah.
and another valid function will be like n minus 1 if 3 divides n minus 1, and n plus 2 otherwise. Okay,
Yeah.
so those are two valid functions, and you have n plus 1. And disclosure, those are the only three valid functions.
Oh,
Okay, I
mhm.
think. I think. Okay, so now we'll just look at this case. Okay, we'll just look particularly in this case, and we'll try to explain what part two, or like question B, is. What does this? Oops. What does this really mean? For example, if I start at 1, uh, for this function, n minus 1, 1, 3, 0, 2. Yeah. So now if I look at this function, f of 0 is equal to 2, f of 2 is equal to 1, and f of 1 is equal to 3. So this is what I mean by I can partition 0, 1, 2, 3, 0, 1, 2 into this sort of set, which is 0, 2, 1. And now I just have that. This thing maps to this thing, this thing maps to this thing, this thing maps to this plus b, plus 3 is f of this thing. F, this is by f, this is by f, and this is what we have. Okay. Meanwhile, if this was like till say 6, okay, then I could have like, one maps, so like this thing, and I'll have 3 goes to, so like it'll be pretty similar, and 4 goes to 3 goes to 5 goes to 4 goes to 9. So n plus 2 if 3 divides n, and it's n plus 5 if 3 divides n minus 1. So for example, this is a function that has like, so for example, 3 goes to 5, 5 goes to 4, 4 goes to 9. Okay, so this goes to 9. 1 goes to 1 goes to 6, so this goes to 6. 0 goes to 2, goes to 1, goes to 6. Okay, and probably going to need to do something. This wouldn't directly work, would it? 2 1 6. Oh no, it does directly work. Obviously, what am I saying? Yeah, so this is fine. This is fine. 8 goes to 7. Yeah,
Yeah, 8 goes to 7.
so
7,
this is a
7
valid
goes,
function.
yeah, 7 goes to 9. Yeah.
7 goes to 7 does not go to 9. 7 goes to 12. N plus 5.
Oh, right, right, right. Now we have new
Okay,
function.
so this is nice because now I can partition this at 1 2 3 4 5 into these two sets, 0 1 2, and then 0. Yeah, yeah, 0 2 1. So I partition it like this: 0 2 1, and then 3 5 4.
Mhm.
Okay, so now 0
Yeah.
goes to 2, goes to 1, which goes to this thing plus 6. Meanwhile, 3 goes to 5, goes to 4, which goes to 3 plus 6. Plus 6 is this thing's f.
So this would happen for all multiples of 3. So I could have 0, 0, 2, 1, and 3, 5, 4, and then 6, 6, 8, 7.
Yeah, yeah, yeah. So that's what we want. We're looking at partitioning the set 0 till 5. Okay,
Right.
so that's why. That's all. That's why. Okay, so yes, it's so my claim is that I can stay within the set alone, like within just 0 till b minus 1, and that
Yes,
will
yes.
do whatever I want it to do.
Yeah.
Okay. I think we're overrunning class time.
Oh, someone's asking for the Miro file.
Someone's asking for the Miro. Oh yeah, I'll share the Miro. I'll share the Miro.
I think now everyone's using Miro because Jams closed.
Uh, yeah, Miro is nice. I mean, I like Miro. Mm,
No, right now, like I think in December or November, Google has closed its Jam.
oh. Mm. Okay, I'm probably gonna leave this as homework. Because we are decently past class time. We're like 12 minutes past. The sketch of the proof is that uh yeah. So now if f of a is f of a is less than equal to 2023 times k, then is less than a. Okay, implies f minus f of a minus 2023 k is f of a minus 2023 k, which is less than equal to 0, which is uh, less than 0, which is a contradiction. Okay, this is the brief sketch of why this is true. Like, try to use this fact. So you want to use this fact to show that, you know, this is true. So basically the idea is that because of said fact, you'll start at some point. So you'll have some elements which are less than 2023. So you'll look at your chain. You'll have some elements which are less than 2023, and you'll have some. Or wait, we're using B here, right? You'll have some elements which are less than B. This will be greater than to B. This will be B, B, B. So BK minus minus pk, which is less than 0. Yeah, you'll have some elements which are less greater than equal to b. So now I just take all the elements greater than equal to b and I start putting them towards the back. Okay, so basically I'm just shifting my entire thing. Like I'll take the last elements from b, so like, and then I'll shift them so that I have only one element which is greater than equal to b, and then these elements will be my ri, and this minus 2023 will be my r1. Okay, that's a sketch. You can work out the proper proof as homework. uh, then what I was initially trying to do is I was trying to build up to this question. Let me see if I can find it. Okay, this is a notoriously hard question, so I wasn't expecting to be able to finish it in today's class, but yes. Okay, so then for this question, what I wanted to do was that I wanted to show some stuff like uh, f of f4 of n is equal to n plus constant. Okay, and then I wanted g of, yeah, I think g of n equals f of n plus 1, and show that g square n is equal to n plus constant. And then I wanted to show that c equals 4, and then from there conclude that there, find all solutions. Find solutions from what we did before. Okay, so this was what I was trying to do. So we'd be using this property very heavily, like property b. We'll use property b heavily, and we'll use property a little bit, and we'll be using property b to like figure out what are possible, paths for this to take. So for example, a obvious solution here again is f of n equals n plus 1, but there are not so obvious solutions which I will leave for you to find out. This is IMOSL 2013 A5. Honestly, one of my more favorite questions, uh, which is why I chose it for today's class. But it's pretty difficult, so I was trying to use these facts from here to build up to this. But yeah, arrows is not dead. We had it like 9 years ago, no, 12 years ago. So yeah, it's a cool thing. It's a cool thing. And it definitely gets used like even more frequently. Like I was doing a BMO problem where I used arrows, um, and such. So it's nice. It's a good topic to know. I'll see if I can do another class on it because I'm not fully satisfied with how much I covered either. I'll share the Miro file. Sorry if the last segment was rushed. So if you have any doubts, you can ask right now. Can you all hear me?
Yeah, yeah.
Okay. Do you guys have any doubts on the last segment, like where I rushed through the sketch of this proof, sketch of how to use this proof to show part B, and then the question, and then a generic walkthrough of the question?
Yeah,
Because
I think for the sketch until we actually try it, then it's not the point yet. So yeah, you have to try was working out. Although the
okay,
sketch seems pretty clear.
okay, the sketch is pretty clear. Then I'll definitely share the Miro by like tonight. Just remind me if I forget as well.
Yeah.
You can just always ping me on the Discord. Okay, I'll share the Miro link by the Miro board. I'll just share it as a PDF by tonight. Uh,
Okay.
yeah, it's pretty chaotic. It was not an organized Miro, but
They're never exactly. I haven't seen an organized mirror.
yeah. So it's an organizing tool, guys. Like it's an organizing tool. Yeah, I mean Miro's advertises itself as like a tool for organizing and coming up with workflows and all of that.
Oh,
So
really?
yeah, like I mean, if you ever make a new me robot, they'll be like, these are some templates to help keep your things organized. I've got blank template. We're going to be chaotic today. Uh,
Yeah, you
every
just
single
need
time.
space to write.
Yeah, you just need space to write. That's the idea. Yeah, I mean, officially class is over now. If you guys have any doubts, feel free to ask, especially on the last segment because very rushed again, lack of time. Yeah.
Yeah, I don't think so.
Okay. Thank you so much, everyone. Bye bye.
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 The recording. Share. Oh no, recording isn't stopping.